Imagine a roller coaster car speeding along a twisted track, when suddenly we freeze it right at the very apex. At this exact frozen microsecond, which direction is the track actually pointing, and what is its precise steepness? By the end of this lesson, we will transition that visual intuition into exact mathematics. We will learn how to locate the peaks and valleys of a curve and define the straight line that captures that instantaneous steepness. To follow along, you will need a basic grasp of algebra, factoring, and how to use the power rule to take simple derivatives. Understanding tangents and turning points allows us to analyze a moving curve and precisely measure its direction at a single, isolated point. The challenge with curves is that their steepness changes at every location. Standard algebra calculates slope using 2 points, but that only gives us an average steepness across a distance, not the instantaneous slope exactly where we are. Look at this graph showing a generic curve. If we place 2 distinct points on it, P and P1, and connect them with a straight line, we create a secant. This line represents the average slope between these 2 locations. To find the steepness at a single location, we use a limit. We move the second point infinitely closer to the first until the distance between them shrinks to 0. That perfectly balanced straight line touching our curve at exactly 1 point is called the tangent, and its slope is exactly equal to the derivative, dy over dx, of our function. The derivative is the physical steepness of that tangent line. It turns a shifting, curving path into a concrete, measurable direction. Let's apply this to find the exact horizontal locations where a curve peaks or bottoms out. We will use the polynomial y equals x cubed minus 3x squared minus 9x plus 27. Think about the very top of a hill or the exact bottom of a valley. At those specific locations, the track flattens out completely. If the tangent line is perfectly flat, its slope is exactly 0. Let's break down this equation on screen. First, we take the derivative, giving us 3x squared minus 6x minus 9. Next, we set it to 0. By factoring out the 3, we get x plus 1 times x minus 3 equals 0. This gives us our solutions, x equals -1 and x equals 3. These 2 x values tell us the exact horizontal coordinates where our original curve might change direction. Setting the derivative to 0 acts as a mathematical metal detector. It scans the entire curve to isolate the exact moments where upward or downward momentum is neutralized. However, we need to be careful. A derivative equaling 0 does not guarantee you found a peak or a valley. Take a look at this graph of y equals x minus 3 cubed. The derivative is 0 at x equals 3, meaning the tangent is horizontal, but the curve simply plateaus briefly before continuing upward. There is no peak and no valley. To verify true turning points, we use a sign check. We map our previous x values, -1 and 3, on this clean number line, which divides our space into 3 separate test zones. We plug a test number from each zone back into our derivative to check its sign. If the derivative goes from positive to negative, the slope shifts from up to down, forming a peak. If it goes from negative to positive, the curve shifts from down to up, forming a valley. Once we confirm the turning points at x equals -1 and 3, we plug those values back into the original equation to find their exact vertical heights. This gives us a maximum at -132 and a minimum at 30. The sign check isolates true turning points from temporary pauses, providing a reliable test for where the function actually changes direction. Let's complete our final objective. We want to write the specific algebraic equation for the tangent line resting on a new curve y equals x squared minus 4x plus 2 at the coordinate 1, -1. First, we calculate the slope at that location. We take the derivative, getting 2x minus 4, and plug in our x value of 1. This gives us a precise slope of -2. Watch how these values drop into the point slope formula on screen. We combine our slope of -2 with our coordinate of 1, -1. Expanding and simplifying this gives us our final equation, 2x plus y minus 1 equals 0. We have successfully reverse-engineered the curve's geometry, forging a custom straight line that perfectly mimics the original trajectory at that exact location. Now, let's bring all these pieces together. We start by plotting our new quadratic curve and pinpointing our target coordinate at 1, -1. Next, we draw the exact tangent equation we just calculated. 2x plus y minus 1 equals 0, intersecting the curve. Look at this graph showing our curve and tangent line intersecting. If we zoom closely into that specific coordinate, the curved line visually flattens out, perfectly overlapping the straight tangent line. The logic holds. The graph flows to the derivative yields the tangent slope, and that tangent slope exposes the turning points. Through calculus, we see that up close, even the most complex curves are ultimately just a series of measurable straight paths.